So now we'll take a look at a second example where we have a 3,000 horsepower motor. And this is the same circuit I did some of the DER examples on. So basically, we've got the substation here at the bottom left. We've got the machine connected up. Basically, it's location D3 in this case. And then we have another location we're interested in looking at voltage sag at, which is going to be at D4. So the customer is going to have a 5 MVA transformer, 6% impedance. We'll assume that the substation value is 0.07 plus J, 2.5 ohms at the 22.86 kV bus. And as far as the way we can view this is similar to what we showed before. You got the substation, you got the line impedance up to the location where we have the motor. We're modeling the transformer in series with the motor. This is going to be the locked rotor impedance. And then we'll go ahead and neglect the voltage drop due to load in our hand analysis, but then the WindMil program is actually going to include this. And so between D3 and D4, if we did this by hand, these voltages would essentially be the same because we're neglecting the voltage drop across here. Similarly, if I'm going to look at this side on the adjacent feeder, if I neglect the voltage drop here, we were just basically interested in getting the substation bus voltage. If I do this calculation in WindMil, basically I would be putting in the line values just like we did before for the project part 1. In this case, in order to get the impedances and try to get this to match up with the simulation, what I'm going to do is get a positive sequence impedance. Unfortunately, WindMil doesn't give that to me directly, so what I need to do is I take the average of the diagonal terms. That gives me a self-impedance. I take the average of the off-diagonal terms. This gives me a mutual impedance. It's like I'm transposing the lines. And then Z1 is going to be ZS minus ZM. And so the value for the line impedance is 0.197 plus J, 0.624 ohms per mile. Okay, so anyway, here's the impedance view one more time in our model. And what I'm going to do is I'm going to take this information and come up with the required impedances. So we'll start with the locked rotor impedance. So what I've got in this case is, let me go ahead and get the pen set up for this. What I've got is I got the 3,000 horsepower motor. I don't have a lot of information in this case. I have to start using some of my approximations. And so I'm going to assume I'm going to have 1 kVA per horse or 1,000 volt amperes per horse. In this case, if I have a 3,000 horsepower machine, what this means is the rated kVA input is going to just be simply 3,000 kVA. To get the full load current, I take the 3,000 kVA, I divide through by square root of 3 times 480. It's a 480 volt load, and I get 3,608 amperes for the full load current. If I assume the locked rotor current is just simply 5 times full load, then this gives me the locked rotor current of 18,042 amps. To get the locked rotor impedance in per unit on the motor base, then this is going to be J times 1 over locked rotor current over full load current. And this is going to give me a locked rotor impedance of J.2. Actually, if I just took the inverse of 5, that would give me the same value. All right, so this gives me the per unit impedance of the machine at locked rotor condition in per unit ohms. Now, I got to convert all my values to a system base. And what I'm going to choose for the system base in this case is 100 MVA. This is a typical transmission base. The voltage base is going to correspond to the nominal voltage at the substations was 22,860 volts. And then this is going to map to a 480 volt base on the customer side. But why would I choose 100 MVA? Well, I could choose any value I want to, right? If you really were to do some thinking behind what value to choose, what you would want to do is you'd want to get values of current probably at the substation that would correspond to about 1 per unit, right? So that would kind of makes sense because I don't want to be working with per unit currents that are like hundreds and thousands. On the same time, I don't want to be working with per unit currents that are like values like 0.00001, right? So you typically would choose a value of S base that for nominal conditions would give you values of current around 1 per unit. So anyway, this is an arbitrary choice, but it's a common choice that's made for like transmission analysis. Maybe for distribution, I would choose maybe 1 or 10 MVA if I were going to do this over. So the substation, I've got this impedance in ohms. I got to divide through by the impedance base. Since it's on the 22.x 6 kV side, I'm going to take kV squared divided by MVA for the power base. And this is going to give me my value for the substation value in per unit ohms. For the line, I've got a distance of 1.91 miles. Multiply that line impedance per mile I just got out of MilSoft for positive sequence, normalized by the same base impedance, and this gives me the line value on the consistent base. Then finally, for the transformer, that's going to be 6% or J.06. We're going to neglect the resistance in this case, and then I just simply have to use the change in base formula where I multiply this value by the new base or the old base. The new base is 100 MVA and the old base is 5 MVA. So this gives me a transformer value of J1.2 per unit. Finally, for the motor, I take this locked rotor base. The machine base is 3 MVA. This just simply corresponds to the normal volt amperes machine's drawing. So to get this on the new system, I have to multiply by the ratio of the new base or the old base for 100/3. And this gives me the locked rotor impedance on the new system base. And then finally, to calculate this locked rotor current, it's just simply going to be the substation voltage in per unit. I'll assume it's at nominal for lack of anything better. And note what are the dominant terms in the denominator. The dominant terms in here are really the motor impedance, and after that would be the transformer impedance. Note this transformer impedance is like 2 times as large as the substation impedance plus the line impedance combined together. So this transformer impedance is essential to getting this number right. And so this gives me a value for locked rotor current that has a reactive magnitude of about 0.116 per unit amps. And I've got a little bit of a resistive part in here, but you can see for the most part, this is a reactive current draw. So when I convert this back, I'm going to use a different technique in this case. If I want the voltage at the motor, I take the locked rotor current times the locked rotor impedance, multiply by the base voltage at the customer site. This is Fourier divided by square root of 3 for line to neutral value. I get 215.5 volts in this case. And if I were to divide that by 277, what we would see is this is a drop of minus 22%. So these other loads that are directly connected in parallel with the customer with the big motor, they're going to see a substantial voltage sag, and there's probably not much you can do about that. Now at D4, which is downstream, we're basically going to get the same voltage that you see at D3 because we're neglecting load drop. And so if I take the transformer impedance times the locked rotor impedance, the transformer impedance plus the locked rotor impedance, that quantity times the locked rotor current, multiply by the voltage base, this is going to give me 254.3 volts, which if I have a base voltage of 40 divided by square root of 3 corresponds to a drop of minus 8%. And so this is pretty substantial on the feeder that has this sag. If I'm below this point, if I'm below the point D3, I'm going to see a pretty big sag. And so, you know, the utility might make this customer at D3 do something about this. They may have to put in some sort of a starting box or supply reactive current locally or do something, because this customer downstream at that point is really going to suffer as a result of this. So 3,000 horsepower is a pretty big motor. At the substation, then you could do this a couple ways to get the substation bus voltage. Either I could take the substation voltage and subtract off the substation impedance times the lock rotor current, or I could just simply work back from the motor, take the summation of all the impedances, sum them together. This time I want this on the primary voltage side. And so this is going to be giving me the voltage of the substation, which we see as a 6% drop. So pretty substantial at the substation bus on the adjacent circuits as well. So this is a pretty substantial sag. But the numbers to keep in mind would be the minus 22%, the minus 8%, and the minus 6%, because we're going to compare this to WindMil. So in WindMil, what you would do is you have this circuit set up. You can run the voltage drop analysis before you see the load put in. You can see the voltages are around 120 volts or so. And then you would put a motor model in at this particular point. And so what we want to do is we want to set this up. We want to set this up for a starting calculation. And so we put in the size of the machine. We put in our power factor. We put in our efficiency. So I'm kind of guessing at this. It's a horsepower. We're going to specifying everything in terms of horsepower in this case. And what we want to say here is for the locked rotor calculation, we want to put this in locked rotor. So you can have this in normal condition or you can have this in locked rotor condition. We want to do a startup calculation. So we got to put the status in locked rotor. The other thing I can do here too in another tab is I can put in the NEMA type. And what this will do from a built-in table is this will give me the ratio to use for lock rotor kVA per horsepower. And so once this is in, then I could do the motor startup analysis in WindMil. And so this is another type of analysis similar to voltage drop analysis. And what we see in this case is we get a flicker of a little bit more than 22%. We get a percent sag on the primary below where this motor's at of a little over 8%. And then we get a sag at the source of about 6%. So this matches up pretty close to our by hand analysis, but this is probably a little bit more accurate because it would include things like the voltage drop due to load and things like that. And then you also get a report. And so when you do the motor start analysis and it gives you a report, and then basically the important thing you're looking at would be what is this percent flicker on my phases at different locations in the circuit. In this case, this report is telling you what this is going to be at the motor. And so again, if this is too large, then the customer would maybe want to put in some sort of motor startup current mitigation for this. Now, another thing, one more thing you may be looking at, and you're not responsible for this on the homework, but you may also want to look at how long is this going to last in seconds. And this isn't modeled in WindMil, but other programs like ETAP would have a motor startup duration calculation. Essentially, it runs a dynamic simulation. And in order to do that, we need to know the inertia constant of the machine. This is sometimes referred to as J. And you have a relationship between angular acceleration, inertia, and torque, where developed torque, this is electrical torque minus a load torque, is equal to this inertia constant times acceleration. So this is a differential equation. And if I have a relationship for the load torque as a function of speed, what I can do is I can solve this differential equation to give me speed as a function of time that I could use to figure out, well, how long does it take for this machine to actually get going? When you do the simulation, I've got some numbers here, and this isn't a very big machine. This is a 100 horsepower machine, but we'll assume the load torque's just a constant to keep this kind of simple. And what you'll see is that the speed starts out at 0, and it takes a while to get going. But once this thing gets going, it rapidly speeds up, and then it goes into a steady state speed that in this case corresponds to the slip of 0.03. Initially, you see the current's rather large, but then when you get close to the operating speed, then the current really drops off dramatically to a steady state value. And you see in this case that, again, the startup current is even greater probably than 5 times the normal load current. The other thing you can look at too is what's going to be the impact of voltage at the motor. And you can see initially there's a large sag, but after a period of time, it goes back up to normal. And so you can see it takes about 4 seconds for this machine to get going because the inertia is kind of large. Then also too, we have this kind of a big constant low torque, which makes it harder for the machine to start up. So we would still get, in our hand analysis, we would still get what this worst case current, what this worst case voltage sag would be. But what this solving this differential equation gives us, it gives us the time it takes for this machine to get up to speed. It gives us the duration of the sag, and sometimes the duration of the sag makes a huge amount of difference. So anyway, if you want to run this, this is the Matlab code for this. And so again, other programs like ETAP and other codes that are more industrial oriented will a lot of times model the dynamics and give you the time to start up as well. Another topic that's associated with power quality is harmonics. And basically these are the non-fundamental, non-50 or 60 hertz quantities that we're going to see in a circuit that are due to a variety of different things we'll be discussing in just a little bit. And these frequency components are generally at integer multiples of our fundamental. So if we have a 60 hertz fundamental frequency, these harmonics are going to usually be like at the 3rd, the 5th, the 7th, the 11th, 13th, etc. But the 3rd would be like 180 hertz. So this is a common harmonic that we would see in distribution circuits. Many times this content, just because you have harmonics doesn't mean that anything bad's going to happen. It just kind of depends. So it kind of depends on the magnitude of the harmonic currents. It kind of depends on the impedances of the circuit. So whether this is going to translate to large harmonic voltages, and it depends on how sensitive these loads might be to having these harmonics in the circuit. So ideally, if we had a linear circuit and we just have resistance, inductance, and capacitance, then if I have a sinusoidal source, I always get sinusoidal currents. And so for a linear circuit, I would not see harmonics. And so if I have a sinusoidal voltage, I get sinusoidal current. Now, I might have a difference in magnitude and phase shift to look at, but the load current is sinusoidal. And so up to this point, we've been assuming everything is sinusoidal and nothing will generate harmonics as a result of that. However, if I had a nonlinear load, if I took this sinusoidal forcing function for this voltage and I had this nonlinear load, then I might get a pattern for the current that looks like this. It's very erratic in nature, where it's very peaky, and we get a couple peaks per half cycle in this case. And so this is the case where we have harmonics. How do we quantify this? Well, a lot of the quantification is based on doing Fourier analysis. And so it was shown a long time ago that if I have a periodic waveform that repeats itself, that I can take a distorted voltage and current, and I could represent this voltage or current as a summation of not only the fundamental, but higher order harmonics. And so this is sometimes referred to as the Fourier series. These components are going to be of integer multiples of the fundamental. And these integer multiples is what we refer to as the harmonics. So the non-60 hertz or the non-fundamental are the harmonic terms. And if we do a Fourier transformer analysis, then we can get the magnitudes and angles of these harmonics based on raw data, based on measurements. So as an example of this, let's suppose we took this waveform I showed you, and this is from a 6 diode rectifier AC to DC. If I did a Fourier analysis on this, what I would see is I've got a 60 hertz quantity with a magnitude of 106.55 amps at an angle minus 9.6 with respect to the voltage reference being 0 degrees. There would be really not much second or third harmonic or fourth harmonic. If I look at the fifth, at the 300 hertz frequency, I've got a magnitude of 41.14 at an angle 124 degrees. And at the seventh harmonic, which is 420 hertz, I've got a magnitude of 13.7 at an angle of 76.7 degrees. So if I were going to write this current using a Fourier series representation, then I've got the magnitude of the fundamental. I can represent this as a cosine times 2 pi times 60t minus the phase shift. I'm going to have the fifth harmonic component. To put this in the time domain, I take cosine times 2 pi times the frequency times t. This has a phase shift of 124.4 degrees. And similarly, I've got the seventh harmonic, which I can put into a time domain form by taking the magnitude of 13.7 times the cosine of 2 pi times the frequency times t plus 76.7. And there's higher order terms on here I'm just neglecting for now. What makes harmonics more or less worse is what's the system impedance I'm injecting into. So if I had this load current, and this load current's actually going downward in this case because it's a load, the voltage at this point is going to be whatever the source voltage is minus the system impedance times the current. And so if I took this waveform, if I had some typical impedance, if I took this current waveform, what I would see at the load would be this. And I could see that the load impedance has been corrupted by the harmonics. I mean, so the load voltage has been corrupted by the harmonics in the source current. So this is what's happening in real life, that if I have one load here at this bus, that all the other loads are going to see this voltage that's not going to be sinusoidal anymore. Here's some examples of some field measurements that were taken in the field. Actually, this is kind of a while ago, but anyway, this shows for a rectifier type of load. This is a motor drive, an old style motor drive. You could see actually these notches in the current. So this was an input for the machine. In this case right here, you can see these are time varying a little bit because the machine draw is changing. So that's actually changing the currents. And you can see what this is doing at the load is causing some distortion in the load voltage. And so in this case, it's actually kind of causing the tops of the voltage waveform to kind of be clipped or flattened a little bit. And this could be an issue if you have loads in parallel that are sensitive to this change in voltage. How do you quantify this? Well, one way we quantify this is through a calculation called Total Harmonic Distortion, where if you take these magnitude terms of the harmonics and you take each one of the harmonic terms, if you square it, you sum them all up with respect to the other harmonics, you take the square root of that. If you normalize that by the magnitude of the fundamental current, that's what's referred to as the total harmonic distortion. We sometimes multiply this by 100%. We get this in terms of a percent. So a lot of times this is a percent THD. When you see this number, you know, you see the number like 3%, 5%, 10% THD. If you want a relationship, you know, what the RMS current is going to be, the RMS current is actually the square root of the sum of all these quantities squared. And so this is also going to be the magnitude at the fundamental times the square root of 1 plus the THD squared. So remember what the RMS current actually has, the root mean squared current actually has. It actually has all the harmonics included in there. Unfortunately, this is just physics. It's not matter whether it's fortune or not, just physics. But basically, it's only the 60 hertz or the fundamental component of that current that's corresponding to any real work, say in case of a motor. If you have a motor and there's harmonic currents, that's just going to contribute to heat. And so it's kind of the harmonics are kind of a waste product, which could potentially damage the machine if the I squared R losses get too high. And here's just a sample calculation of the THD, where if I took the square root of the 41 squared plus the 13.7 squared and divided by the 106.5, this would be 0.41 or 41%, which may or may not be bad. I mean, it just kind of depends on what else is going and what the source impedances are. So depending on the stiffness of the system, we would just have to kind of wait and see to what degree this might cause a lot of issues with distorting of the voltage. Okay, so I'm going to go ahead and stop this segment here, and when we come back, we'll talk about some sources of harmonics and how harmonics propagate, and just do a real quick numerical example.